Hello everyone, welcome back. We are here with the question number 6. This question was from Ionic Equilibrium. Actually, it was based on simultaneous solubility. And some salt was given as Mx. This was present in some acidic solution. pH was defined as 2. Now, we were asked about what was going to be the pK of acid when under two different conditions, the difference in the solubility was given to us. Okay, as usual, we are saying this is most elaborate video solution available on internet for this question. You can witness itself. This is IIT JEE 2023 paper number 1 held on 4th June 23. We are discussing this is paper number 1. This question is from section 2, which was only one option correct. Here we go. The question was on decreasing pH from 7 to 2, that is from neutral to basically making it acidic. The solubility of the sparingly soluble salt, which was some Mx salt, was given to us of a weak acid. So this salt is basically coming from some weak acid and strong base, we have to assume. This solubility was supposed to be increased from 10 raised to power minus 4 to 10 raised to power minus 3 moles per liter. Now, when we have done so, what was the pK of the acid? So this is basically we are having the change in solubility of the sparingly soluble salt as a result of change in pH. Neutral solution being made acidic, that is what we are saying. This is the case of simultaneous solubility, because if H plus ion concentration is going to be changed, the H plus ion coming from the external source, which is changing the pH, versus the H plus ions which can be present in the solution due to the salt Mx, that we had to decide. These were the options. Moving forward, we are talking about solubility first. What this means, very much clear. This thing is, we have different situations. A number of times we are representing this solubility in grams per 100 ml of the solvent, 100 grams of the solvent. We can define this as the maximum amount of the solute which can be dissolved in the given amount of solvent. Solvent should be defined actually, and this is under given conditions. And when we are saying these conditions, importantly, temperature should be defined, because solubility changes a lot when temperature has been changed. So how much solute we can put in a given amount of solvent, that defines the solubility. Commonly, we are representing this as grams per 100 ml of the solvent. That's the relative amount of the solute in solvent. In chemical perspective, we'll mostly be dealing with the unit which is moles per liter. So the moles of the solute present in 1 liter of the solvent. And basis on this, we can classify our substances into these two categories. One, which are highly soluble. These compounds will be having relatively much higher value of the solubility. And the second one is insoluble, which are actually sparingly soluble salt. They will be having limited solubility. There is nothing like which is completely insoluble. Whatever be the solute, whatever be the solvent, some amount of it can still be going. That amount may be sometimes such small value, we can not have the experimental verification possible, but this is going to be soluble. So rather than saying insoluble, the better term would actually be sparingly soluble. And this is what we are talking about when we are talking about the KSP values. Okay. Once again, we are talking about what the solubility is. This is basically ability of a substance, that is a solute, to be dissolved in a given solvent. So this ability will depend upon the solvent and the solute. As you change these two things, this will be changing. Solubility will be determined experimentally, and the solubility data we usually plot against a function of temperature, and those plots help us understand in different aspects like in chemistry, in pharmaceutical industry, environmental sciences, and different cases. This is one such plot where we are seeing solubility is given in terms of the grams per 100 ml of the water, and the temperature is kind of changing from 0 to 100 degrees Celsius. So these different kind of solutes will be having different solubilities. We have here the list of solutes. So sucrose, ammonium nitrate to potassium sulfate, there are different values of the solubility with different temperature. As temperature is changing, solubility is changing. As solute is changing, solubility is changing. And we have kept the solvent as water in all these cases. So this is clear enough to say that solubility will be changing with the change in the solvent and change in the temperature. That's more important factor. Other factors will also be dealing with. So here we are having some solubility curves, and as we can see, most of the ionic solids we have taken here, they are having a positive slope, which means as temperature is increasing over here, solubility is going to increase. Again, solubility we have taken in grams per 100 gram of the water. So majority of the ionic compounds except these two, cadmium selenate, cerium sulfate, and a few salts of calcium which we know like calcium nitrate, they are having the situation other way around where solubility is going to decrease with temperature. Majority of the compounds like sodium nitrate, cadmium chloride, potassium nitrate, magnesium chloride, potassium chloride, for most of these solubility increases with temperature. And if we compare the ionic compounds which are given in this curve, NaCl is having very small change, which means if you are heating the solutions of NaCl, you'll find very small change in the solubility. But on the other hand, if you change it for KNO3, small change in temperature will be changing a huge amount of solubility for any given range, starting from 0 degrees Celsius to this data which is for 50 or 60 degrees Celsius. Keep on changing temperature, that will be changing in much greater magnitude. Cadmium selenate, yes, that we're talking about. This is going to have the negative change in the value of solubility as temperature is being increased. We can be talking how temperature can be changing the solubility, but this is in general how some ionic compound and different ionic compound can be having differences in the value of the solubility as temperature is changed. Moving on, we have nature of solute and solvent, which can be governing the solubility of these different compounds. So the first and foremost thing we'll say ionic or covalent, that will be deciding whether this is going to be soluble in a given solvent or not. More importantly, water. In general, we say ionic compounds are soluble in water, and organic compounds are soluble in organic solvents like ethyl alcohol, ether, or carbon tetrachloride. It also depends on whether your compound is solid, liquid, or gas, because gases will be having very little interactions with the given solvent, so that solubility are going to be relatively on the lower side. Solids and liquids, on the other hand, will be having relatively greater value of the solubility for any given solvent in general, because they're already having relatively stronger interactions possible with any other substance. And because they are solid and liquid, that implies they have relatively greater tendency to get associated. Temperature is one thing what will be changing as our nature of the compound is becoming exothermic or endothermic. So when we say exothermic or endothermic, basically when you are dissolving something in water, whether heat energy is being absorbed or released, that can be changing the situation, that can be changing the amount of solubility, what is happening, whether it's increasing or it is decreasing. Pressure has very high change for gases because there is a huge change in volume observed. For solids and liquids, the change in pressure is relatively much smaller. Then we have got the other factor, which is presence of other solutes or other impurities. We have converted this into some smaller factors, that's common end effect, simultaneous solubility, and the complexation effect. Sometimes we can be calling this reactive ion pair effect. This common end effect and reactive ion pair effect are kind of the two extremes. One works one way, another works the different way completely. Simultaneous solubility can be the case of common end effect, or sometimes it can be just a simultaneous ion present. When this is not a huge differences in the solubility of the two different compounds, it cannot be called as common end effect. Then we call it as simultaneous solubility. Okay, now going to these points one by one, what we talked about earlier. First one is factors affecting the solubility, which is going to be the nature of the solute and solvent. So when we say nature of solute and solvent, there's a rule of thumb which says like dissolves alike, which means one kind of substances will be dissolving very easily in the same kind of solvent. So to expand it further, we'll say ionic compounds tend to dissolve more easily and more polar, which are usually inorganic compounds. And this is again a generalization, because if you take the example of calcium carbonate, although it is inorganic, it does not dissolve in water. If you take NaCl, it does so. The question will be, how do we know, or what is the factor governing? There are two important factors, we'll say, which are governing the fates of the ionic compounds as far as solubility is concerned. So one is what we are calling as the lattice energy, which is the tendency to break the ionic bonds, like how easily ionic bonds of a given ionic compound can be broken. That is measured by lattice energy. And second thing is hydration energy, when we are talking about the solubility in water. If it is in general any other solvent, we will be calling this term as the solvation energy. So solvation energy versus lattice energy, these two things will be governing our overall solubility for any given ionic compound. And we have got example. So the idea is, if the lattice energy is less, solvation energy is more, then our compounds will be tending to be more and more soluble. If things go other way around, like if lattice energy is more, meaning more energy is required to break the bond and less energy is released when they are getting solvated, when they are getting hydrated, then things are going to be insoluble. So for calcium carbonate, the situation was that lattice energy is lying onto the higher side in comparison to hydration energy. And for calcium chloride and calcium nitrate, if you say, situation is that lattice energy is relatively smaller in comparison to hydration energy. So these things are known to be soluble in water. Also, we have other examples where here we have got cation same. Now we are changing the, like in this first case, cations were same. In the second case, we have taken anions which are same. Here, beryllium and magnesium sulfate are known to be soluble in water. Again, we'll say very high hydration enthalpy for beryllium is making the overall hydration energy to be on the higher side in comparison to the lattice energy. And barium sulfate, on the other hand, is going to be insoluble. Here, barium ion being bigger successively, solvation energy term becomes relatively smaller and smaller, and finally we get the situation that barium sulfate is insoluble. So for sulfates, if you go down the group, this is second group, that is alkaline earth metals, the solubility decreases. Before we move on to the other factors, we'll be talking in brief about the thermodynamics of the solution or the thermodynamics of dissolution. So these energy changes are basically two things we are doing here. Number one is conversion of the solute and solvent into the separated particles. And then the separated particles are supposed to be converting back into the solution. So we'll be having two-way changes over here. Number one, endothermic changes, where we are converting these associated states into the separated particles. These are going to be, both these steps are going to be endothermic in nature. When we say endothermic, we means delta H is going to be positive. Although while comparison, we'll be talking about their magnitude, mod values, not just the positive or negative signs. So when these separated particles are converted back into the solution, when this is happening, this is going to be exothermic change, and in this case, delta H is going to be negative. So it turns out to be, if endothermic change and exothermic changes are in such a way that the magnitude of exothermic is greater than that of the magnitude of endothermic, then this thing is going to be favorable change. And if it is not, this is going to be unfavorable change. That's because we need to provide this much extra energy, then only we can convert the things into the solution. Actually, we would have put the solute and solvent terms together. If the amount of solvent is greater and solute is very, very less, then the value can be this much. And it can be ranging basically between these two values from here to here. So unless and until, in the second case, this is case number 1, this is case number 2, unless and until we are providing some external energy to our solute and solvent, the second kind of solutions are not being formed. The first kind of solution, they can be found very easily. That's the meaning of the how the thermodynamics can be playing their roles, so that one kind of change is going to be favorable, another kind of change is going to be completely unfavorable. Now we'll be going back to the factors affecting solubility. We're talking about some rule of thumb, like dissolves alike. Here we are. Now we are talking about the covalent compounds. So when we have got some covalent compounds, they will be having a tendency to get dissolved in less polar solvents more easily. These less polar solvents are going to be organic in nature. So we have got one term for the solubility for such compounds. We say the solute interactions, like if you have, say, taken NaCl, those attractive forces, versus, actually that is not the valid example because we're talking about covalent compounds. So say we have taken the example of naphthalene. So naphthalene attractive forces versus solvent. Say we have taken benzene as the solvent. So naphthalene interactions versus benzene interactions, kind of those attractive forces between naphthalene molecules and benzene molecules. We are comparing these, and if these are going to be comparable, like almost similar to those between solute solvent, so naphthalene versus benzene versus naphthalene benzene, if these attractive forces are comparable, we can take it for granted these kind of things are going to be soluble. That is what we'll be seeing happening in like dissolves alike. Here we go. We know naphthalene is soluble in benzene, but naphthalene is insoluble in water because the attractive forces in water are much greater in comparison to attractive forces between naphthalene and water. So water does not want to get associated, because if it is happening, water will be not having that much stability. It needs to acquire much higher energy coordinate. That is not going to happen on its own. So naphthalene does not dissolve in water. We have another example where sulfur is soluble in carbon disulfide and in benzene, but this is insoluble in water. Once again, same reason is going to play. That is, sulfur having covalent bond, carbon disulfide having van der Waals forces which are not very much polar in nature, both the sulfur and carbon disulfide are known to be non-polar molecule, they could have dissolved something which is non-polar. So that's why sulfur is being dissolved in carbon disulfide, which is non-polar, and even benzene is non-polar. Water being polar will not be getting easily mixed with sulfur. Also, there is another factor which is hydrogen bonding, which can be changing the play of the organic compounds completely. If our organic compound can have the possibility of hydrogen bonding in spite of being organic compound, they can still be soluble in polar protic solvents like we say glycerol or ethyl alcohol. Although it is organic, it is insoluble in benzene, you know that, and it is soluble in water. Again, this is going not just to one kind of thing, that organic and inorganic or organic versus inorganic. This is going to going about their attractive forces, their nature. So when glycerol is put in water because of extensive hydrogen bonding, this is getting dissolved. When benzene is put in water, because benzene is non-polar, this cannot have that strong attractive forces as water can have or as glycerol can have. Glycerol can have now associated nature because of hydrogen bonding. It is getting mixed with water. Benzene is incapable of doing so. It is remaining insoluble in water. Another example we are having, number of such molecules in organic chemistry we know which can have hydrogen bonding with water molecules, and they really are known to be soluble in water. We have example of glucose, our table sugar, sucrose, methylamine, formaldehyde, acetone, and number of other solvents which we might have been knowing. We'll now move further. We'll be talking about how temperature is playing its role in the solubility of these different compounds. So the solid compounds, liquid compounds, and gas compounds can be having differences in the solubility. And for solids, actually, if you forget about the nature of the ionic versus covalent, another factor which can be changing the solubility of the solids is the temperature. We have seen that in most of the cases, the solids are having endothermic dissolution, so that solubility is supposed to be increasing with temperature. Very few solids, we have seen few examples like cerium sulfate, cadmium selenate, those were having the situation that solubility was decreasing with temperature. They are different kind of compounds. In liquids, we usually found smaller effects than the solids or gases. Their attractive forces are going to be not changing up to that much greater magnitude, and gases increase in temperature is always leading to decrease in solubility. Here we are having in this curve some of the solids, liquids, and gases. You can see, have a look at sulfur dioxide. Solubility is decreasing as temperature is being increased. NaCl, very little change as we talked about earlier. Most of the other solid compound solubility is increasing as temperature is being increased. Now we'll be going to the temperature, which is most important of all the factors affecting solubility. So for most of the solids, we have got the situation that solubility was increasing. This was the case. We have been seeing this over a period of time. We have seen a number of such examples. And talking about liquids, we have got very small effect because the attractive forces in majority of the liquids are going to be lying onto the relatively onto the same domain, same range, we can say. Solids and gases can be having completely different nature of attractive forces. So if we are having two things which are liquid, the chances are that attractive forces will not be varying by a huge magnitude. So if liquid 1, liquid 2, they are having similarity in their nature, similarity in their attractive forces, temperature may not be changing much of the overall solubility. Although the value of delta H, like their dissolution is endothermic or exothermic, the net result can be figured out. We can comprehend how this is going, whether this is going to increase or decrease as temperature is changed. And for gases, the second diagram over here is all about gases. We know whether it is methane, whether it is oxygen, whether it's carbon dioxide, carbon monoxide, nitrogen, or helium, whatever be the gas, does not matter. You keep increasing temperature, their solubility keeps decreasing. And one of the reason which we can give is very simple. Gases have a tendency to escape from the solution. And if temperature being increased, their escaping tendency will be more and more. If you decrease the temperature, gases can still be made soluble. And we'll say the delta G as delta H minus T delta S is measuring governing factor for these reactions. So delta H may be having whatever value that T times delta S for gases is going to be very, very much dominating effect, because dissolution of gases is going to be entropy decreasing effect. As temperature is increased, this term will make our dissolution relatively less likely, because if entropy is decreasing, delta S sign is negative, minus T delta S is going to be positive. Temperature increased, we are getting more and more positive delta G. So free energy of dissolution of gases is going to be unfavorable with temperature change. That is what we can see in the result. Pressure is the next factor we are talking about, and we have known that if you are increasing the pressure of the gas, then solubility is going to increase. We have known this thing as per Henry's law. Even we have got our general observation when the soft drinks are dissolved in different whatever those different brands are. Carbon dioxide is basically dissolved to make those soft drinks, and all the cases carbon dioxide is known to be dissolved at very, very high pressure. And we can see that as we open the bottle, that fizz which starts getting out of the liquid is because when it was bottled, external pressure was kept very, very high, and when we are opening the cap, external pressure is just 1 atmosphere. So those all extra gases which were dissolved earlier, they tried to immediately rush out of the solution. That is what was happening in the case when we were opening any of the bottled drinks. And this is going to be very important effect for the solubility of the gases. And whenever we are having a huge change in the volume, when you are dissolving something in water, and if volume is decreasing when solution is being formed, as we have this situation, there is going to be very high change in solubility with the increase in pressure. With increasing pressure, solubilities are going to increase. So for liquids and solids which are much less compressible, where we see much less difference in the volume change, there is very, very little change in the solubility for the pressure change. Here we are having another factor which we have been calling as simultaneous solubility. So this is basically the presence of other sparingly soluble salts or other weak electrolytes which can be giving us same kind of ions in the solution. So this is going to be kind of similar to common ion effect, but this is going to be in much smaller extent. So that if you have got common ion effect, you could have kind of neglected the contribution coming from one of the weak electrolyte. Basically in common effect, one of the things is going to be behaving as strong electrolyte, other one is going to be weak electrolyte. Over here, when we are having simultaneous solubility, this is covering all the cases, whether you are having one strong, one weak, or both the weak, or maybe in some cases both as strong. So when we have got two such sparingly soluble salts which share just one common ion, in that case the overall solubility is going to be modified. Say for example, we had got some compound as AX. This was sparingly soluble salt. So when we have put this in water, this is going to dissociate into A plus and X minus. So if there was nothing else present, its solubility can be defined as, say, S, small s. This is for solid, that solubility can be having certain value. Now suppose we have got some another salt BX2 present as well, and this is also solid, putting in large excess of water. This is also dissociating up to a certain extent, and this is also getting B2 plus ions and 2X minus ions. The first one and second one, they were having some values of their KSPs as KSP1. This was having the value as KSP2. Now, if in the beginning the solubility of AX was square root of KSP1 in presence of another solvent, that's BX2, solubility is going to decrease in comparison to KSP1. So this is, we are trying to say, whenever we are having one of the ion common in two different salts, and if both of these were behaving as weak electrolytes, then the solubility either for AX or for BX2 is going to be decreased. That is the case of simultaneous solubility. The one particular type of simultaneous solubility is the case when we talk about common ion effect. So in the common ion effect, what we are having, one of these electrolyte is the weak electrolyte, and this will be having some equilibrium, solubility equilibrium established. Into this equilibrium, say we are talking about lead chloride. So when we have put 4 of the lead ions and 8 of the chloride ions in solution, this is an equilibrium in which lead ions and chloride ions are combining. They are forming PbCl2, and then some of the PbCl2 can be dissociating back, giving us chloride ions and PbCl2. So the final situation we have represented here, which can be kind of related as the KSP equilibrium, 10 of the PbCl2 and 4 of the dissolved PbCl2, which gives you 4 Pb plus ions and 8 chloride minus ions. This thing is present in our solution. And now if we add some NaCl into it, what we have done, we have added 4 NaCl into this solution, into the same solution which was present earlier, this one. So what is happening now? Earlier we were having only 8 chloride ions. Now 4 extra chloride ions have joined in this 8 chloride ions. The total chloride ions have become 12 chloride ions. Now these chloride ions are going to modify this equilibrium. It is a kind of in this equilibrium. Now we are having more of the ions present. So some of the ions are going to convert back into the reactants, because KSP equilibrium will be limiting the product of the lead ions into the chloride ion concentration raised to power 2. So what is happening? Some of the lead ions are moving out of the solution. Here we have that situation. Earlier, because KSP for PbCl2 can be defined as the concentration of lead ions into concentration of chloride ions squared. As PbCl2, as NaCl has been added into this PbCl2, that equilibrium is now going to change in the backward direction, so that you are having now more PbCl2 as the precipitate, less Pb ions are remaining into the solution. So solubility of PbCl2 is being modified when NaCl, any strong electrolyte, is being added into the solution, right? That was common ion effect, kind of extension of the, or just one particular case of the simultaneous solubility, where one of the electrolyte is becoming strong, another electrolyte is taken as weak. So the dissolution of the weak is being suppressed further if at least one of the ion in the electrolyte and the sparingly soluble salt is common. Like in this our given case, it was chloride which was common between these two salts. Moving on, we have got the case as the reactive ion pair effect or the complexation effect. So whenever we are having some complex formation tendency, number of these reactive ions can be present which can form the complex, and if some complex formation is taking place, the equilibrium will be shifting in the forward direction. So what this will do to the solubility, if it was say silver chloride, solubility of the silver chloride will increase if any ligand which can form the complex is also present in the solution. We are taking an example. So when there is AgCl, this is solid, this will be dissociating into silver ions, aqueous, and chloride ions, that's also aqueous. In absence of anything, there will be some solubility which is going to be square root of Ksp for the AgCl. That is roughly 10 raised to the power minus 5 is the solubility, because Ksp of the AgCl is roughly 10 raised to the power minus 10. Now, if we are putting some ammonia, or you can say ammonium hydroxide, into the solution, this ammonia we know as forming a complex, and we should be elaborating that point that this Ksp is going to be, sorry, the equilibrium constant for the second reaction is going to be very, very high. So we are writing here the complex which is being formed between silver and ammonia. This is the complex which is being formed. Although from this solubility equilibrium, it was told that the value of Ksp is very, very less, so silver ion concentration are very small. This equilibrium over here was not lying into the favor of the forward. This was mainly lying in the backward direction. But as these silver ions which have been generated, they are being continuously being reacted with the ammonia to form this kind of complex. That's what calling as complexation reaction. Silver ions keep on moving in the forward direction because of very high K equilibrium value for this reaction. As silver ions are formed, they are converting into this complex. More are formed, more are converting into that. So more and more of the AgCl now in the given solution can be dissociated. We say solubility for the silver chloride, which is sparingly soluble salt, has been improved in the presence of this complexating agent, which is ammonia. Talking about Ksp, which is solubility product constant, it is a kind of equilibrium constant. This is going to be defined as the equilibrium which is being established between a solid compound and its dissolved ions when we are having saturated solution. And as are the other equilibrium constant, they are constant for a given temperature, so that if you change the temperature, their values will change. In general, we can say measurement of solubility of a given compound can be represented by the Ksp, solubility product constant. Although they may not be always true, we will be seeing that in some time. So we have taken some compound which is looking like AB. Its Ksp can be defined as A plus raised to power m, B minus raised to power n. Actually, if this is just AB type, then M and N have to be exactly the same. So A and B are going to be the molar concentrations, M and N can be their stoichiometric coefficients. So this could have been any other kind of ion, we could have related it that way as well. So if you are writing the equilibrium expression for this AB, put in water, this is converting into A plus ion aqueous and B minus ion aqueous. So in the very much beginning, when T was equal to 0, AB we are taking as concentration unity, because solids are not going to have their concentrations changed. Actually, this should have been considered as activity rather than the concentration. So A plus ion concentration was 0 in the beginning, B minus ion concentration was 0 in the beginning. Now as we are moving towards equilibrium what is happening? S from A is being dissociated. So S of the A plus and S of the B minus ion is being formed. Now this A plus and B minus ion what are being generated, they can be related with this equilibrium, because at equilibrium K equilibrium is going to be defined as concentration of A over concentration of B divided by concentration of AB. Because AB is solid, its concentration is supposed to be unity. We can rewrite that K equilibrium into AB as a new constant, which is going to be K equilibrium, which is basically KSP. So these two things put together have been written as KSP. So KSP is going to be defined as concentration of A times concentration of B. This was a general expression for AB kind of compound. Now going to the next one, which we can generalize for AXBY type of electrolyte. Situation is going to change a little bit. Important thing to note is when the 1 minus S is happening over here, because this was AXBY. So A which are being formed, they will be formed X times A. B which is being formed, this will also be going to be Y times. So because 1 mole of A is containing AX and BY, that is how the dissolution of this AXBY is going to be. The result is X times S is being formed as a cation, Y times S is being formed as anion. Now putting the KSP equilibrium over here, concentration of A raised to power X, concentration of B raised to power Y. Now concentration of A itself is X times S, so this is becoming X times S raised to power X, Y times S raised to power Y. Expanding these terms, we'll be having X raised to power X, Y raised to power Y, and S raised to power X plus Y. That is how the KSP expression for any binary salt can be represented. If you know the value of X and Y, we can substitute and we can find the answer. Coming back to the point, as we have been talking earlier, the value of KSPs may not always be giving us the exact information about the solubility. They can be approximate measure of the relative solubilities. If you are having similar type of salt, like similar constitution like A3B2 or A2B3, then you can have a relative comparison possible. If one of these salt is looking like say AB and another is looking like AB2, then this comparison may not be valid at all. Here we have an example. So in general, we can say higher KSP values imply more solubility, but this is only a generalization. So we can have an example over here. So when you are having some compound which is having constitution as AB2, another compound is having constitution as AB, both of these compounds can be having the values of KSP as 10 raised to power minus 10, but that does not mean their solubilities are going to be same. In such a case, AB2 is going to be relatively more soluble in comparison to AB, right? AB will be having its solubility somewhere 10 raised to power minus 5, and AB2 is going to have its value of KSP as 10 raised to power minus 10 divided by 4 cube root of that. So that turns out somewhere 10 raised to power minus 3. This is more soluble in comparison to another one. So that was the case. Now we know that KSP can be determined experimentally by measuring the concentration of ions in the saturated solution, although we have got some alternative methods as we do in the electrochemistry. We can do the measurement of EMF, and we can calculate back the concentration, which can be giving us the value of KSP. We also know conductivity measurements method, where we can know the relative conductance at the given concentration and at infinite dilution. We have seen that question already in this JEE Advanced pattern. We have discussed that question, how that equivalent conductance can be governing the solubility. Now, moving on, we have got again this is to remember that KSP is always going to be temperature dependent, just like any other equilibrium constant. So changing the temperature can be changing the solubility as well. Now, coming back to our original question, we have got here some solvent, which is some solute, which is looking like Mx. And this Mx can be represented in a way that in the very much beginning, when T was equal to 0, this is the situation. Mn concentration is 0, Xn concentration is 0. And when equilibrium is being established, then the concentration of Mx is going to be 1 minus. Basically, that's not the concentration. That is some amount of Mx is being dissociated. So its concentration is still supposed to be remaining as unity. Now, this is the concentration of M plus ions, and this is the concentration of X minus ions. And as we understand its KSP, we can write the value as S square as being the solubility. Now, when we are pH of the solution, we know that pH of the different aqueous solutions can be changing from 0 to 14. Here we have got a small recap. This is basically a measurement of the acidic or basic nature of a solution, and this is telling us about the concentration of the hydrogen ions in the given solution. And also we define this is going to be the negative logarithm of the H plus ion concentration. So that was the definition. We can write this mathematically as pH is equal to minus log H plus ion concentration. And we also understand that when temperature is 298 Kelvin, then this pH scale may be ranging from 0 to 14. So pH is, when pH is 7, we are considering this as a neutral. That is happening only and only if this is the temperature. And below 7, we'll be saying the concentration is going to be giving us some acidic solution. And above pH 7, H plus ion concentration will be in such a way that is going to give us a basic solution. Most common solutions will be having their pH ranges varying between 0 to 14. We have got some common fluids in the next slide, which have got the characteristic pH values for their different solutions. Here we go. This is the neutral solution. We can think about water. As we go on to the left and on to the right, we are having acidic and basic solutions. This battery thing is not actually this kind of battery. This is lead. This is some dry battery. They have shown that we should have here some lead acid battery, where we are using the concentrated sulfuric acid. That battery will be having the value of pH as 0. Normal batteries, which we are having dry cell, their H plus ion concentration is not reaching as much, which can reach to this particular value of 0. 0 pH implies we are having the concentration of H plus ions as 1. So that is not going to be the case in general. Okay, so we have got one extreme where we are having drain cleaners. Like when we get our different drains clogged, then we are having some that pouches which we just pour it open. Those are very much hygroscopic because of presence of sodium hydroxide and other similar things are present over there. Potassium hydroxide can also possibly be present sometimes. Sodium being relatively economical, that is mostly used, and that is actually most frequent composition. So those things basically will try to get clogged. Whatever those clogged organic material would have been, it can dissolve those, because the KH is very strongly basic. There will be hardly any organic compound left which may not be cleaved by this strongly basic solution. That was the case. So and the different cases of these different fluids we are having, we can just have an idea which one is more acidic, which one is more basic. Moving on, we have got the value of pH, which is basically logarithmic scale. It is important to note that when pH is changed by tenfold, when H plus ion concentration is changed by tenfold, then pH is changing only by 1. So here is the example. We have got solution of pH 3. This is 10 times having more hydrogen in concentration than a solution with pH equal to 4. And acids are having relatively higher concentration ions, and bases will be having relatively higher concentration of OH minus ions. So the bases will be having higher value of pH, acids will be having lower value of pH. And also it should be noted that this is applicable only and only for the aqueous solutions. If you are keeping, say, ammonia as the solvent, sulfur dioxide, liquid sulfur dioxide as the solvent, then this pH scale should be accordingly modified. Although we don't talk much of that, we mostly talk about the aqueous solution. Coming back to the aqueous solution, we will be writing that pH as minus of log of H plus ions, and so that we can be also writing as minus log of Kw divided by OH minus in concentrations. Alternatively, we can write H plus ion concentration is equal to 10 raised to power minus pH. If nothing else is present in water, this is pure water, then H plus ion OH minus in concentration is going to be equal. And if this was temperature 298 Kelvin, then both of these values are going to be 10 raised to power minus 10. If you are adding acid or base, then these values are going to be something different depending upon the medium. More H plus ion, it will be acidic solution, and if in any solution H plus ions are more, they will be going to be basic solution. But in none of these cases, either of these values can be 10 raised to power minus 7. Coming to our main question over here, we are having two situations. Number one, it was when pH was 7, that was basically our neutral solution. Another one was when pH was changed to the value of 2. So when pH has been changed to 2, we are basically saying this was an acidic solution. Earlier it was a neutral solution. The H plus ion concentration is 10 to the minus 2. In the first case, H plus ion concentration was this. Now we are putting the situation of simultaneous equilibrium, where one species, which is part of two equilibrium, is going to be considered as in the simultaneous equilibrium. The species which we are talking about right now, that species is basically the compound number, the X minus ion. This one is the species which is the part of simultaneous equilibrium. So this is the first equilibrium, which was originally present when pH was 7. So S was the concentration of M plus, S was the concentration of X minus. Now, when we are keeping this in the solution of pH 2, the solubility is going to change. How this is changing? Because this X minus ion, which is present over here, when we are increasing the concentration of H plus ion, these H plus ions can be combining with this X minus ions, they can be forming HX. And this reaction which we are writing over here, this is the reverse of the dissociation equilibrium of weak acid. So weak acid dissociates up to very small extent, reaction hardly goes in the forward reaction. So this reverse reaction will be going almost towards completion. That is what we are writing here. This reaction will be tending to go to completion because this is the reverse of the weak acids dissociation. So what we are writing here in the beginning, S minus X is the concentration of X ion. 10 raised to power minus 2 minus X is the concentration of H plus ions, and X will be the concentration of HX. Putting this thing back in place, that this reaction tends to completion, X tends to become S, so that you can say that if this reaction is completely going into the completion, then X will keep on increasing and reaching to the finally the value of S. Here we need to apply the simultaneous equilibrium for these two species, X minus ion over here and X minus ion over here. That is what we are saying. Simultaneous equilibrium is present for the X minus ion. This one species, X minus ion, is the part of two different equilibria. So its concentration in one equilibrium over here and its concentration in this equilibrium over here must be the same. Here we have done so. So finally, when pH is equal to 2, its simultaneous equilibrium is going to give us the very same value of the Ksp. We are writing the value of the equilibrium over here. So solubility equilibrium Ksp now is being redefined as S into S minus X, which is originally it was 10 raised to power minus 8, because Ksp is not changing with any experimental condition. This is changing only if temperature has been changed. For a given reaction, Ksp does not change. So this 10 raised to power minus 8 is going to be now equal to S times S minus X. That means the S value, this S value is not going to be the same S value as it was in the beginning. Because if it is the same as 10 raised to power minus 4, 10 raised to power 4 minus something can never be equal to 10 raised to power minus 8, as well as that. Now applying this to the K equilibrium, because the second reaction is the kind of equilibrium that was, we have written 1 by Ka. 1 by K turns out to be concentration of Hx by concentration of H plus and concentration of X minus. Substituting these values, Hx is the concentration X, which can be written as S. This is the concentration of H plus ion, which is, this is concentration of basically X, which is S minus X. This is the concentration of H plus ions, which is 10 raised to power minus 2 minus X, like that. This was 10 raised to power minus 2 minus X, 10 raised to power minus 2. Approximately this can be written as 10 raised to power minus 2. So at the pH 2, now we are having the situation that we have got two expressions. Ksp is defined and K equilibrium is also defined. So we are now multiplying these two expressions so that we can evaluate the value of S. These two expressions we have done. We have basically multiplied these two expressions. So this is becoming Ksp by Ka, and this is turning out to be S square divided by S minus X 10 raised to power minus 2. These values were 10 raised to power minus 2. That is a typo. So this is now going to give us, we can evaluate this expression for S. Ksp by K is turning out to be S square by 10 raised to power minus 2 times S minus X. So S is, we can say this is going to be, S minus X can be neglected if we are saying S minus X is nearly 0, then S can be evaluated to be square root of Ksp divided by 100 times Ka. This is now rewritten as we are taking out the square root of 100 as 1 by 10. This is the final expression of solubility in the case of when pH was 2. We can say this is solubility as S2. Now we can compare this S2 versus S1. So this is the value which we can write as your S2, which we have seen in the problem. It was given that when the pH is changed from 7 to 2, solubility is changed from 10 raised to power minus 4 to 10 raised to power minus 3. So we have an idea that S2 minus S1 is going to be 10 times. Now putting this back into the expression, so we have got S2 by S1, which is equal to 10, and this new value of S2 is this, and the older value of S was square root of Ksp. Rearranging this expression, we are now rewriting. So this is giving us the value of 1 by Ka as, so what we have done is we have cancelled out one Ksp term over here. So this is 1 by 10 times 1 by root of K, that is 10. So that is becoming 1 by square root of K is becoming 100 So it implies that k is 1 by k is 100 square. So k is turning out to be 10 raised to power minus 4. If k is 10 raised to power minus 4, what about its pKa? pKa will be 4 because that is negative of logarithm 4. That is what we were supposed to be calculating. So what we have done, in the first case, the solubility was S1 at pH 7, which was exactly square root of Ksp, this value. When the pH is now 2, solubility is S2. The expression for this S2 is turning out to be 1 by 10 square root of Ksp by Ka. So these two values as per questions were related by a factor of 10. We are substituting this S2 by S1 in the terms of Ksp and Ka, and we are going to evaluate it. So we found that the value of K was 10 raised to power minus 4. That tells us the pK is going to be 4. Coming back to the original question, this question is, on decreasing the pH from 7 to 2, solubility of sparingly soluble salt Mx of a weak acid increased from 10 raised to power minus 4 to 10 raised to power minus 3. We had to find what is the pK of Hx. So we have got enough discussion, very lengthy discussion, and we concluded that pK of the solution is going to be 4. Although the major part of the discussion of our question was based on solubility and solubility product. In the end, we had a brief discussion about pH, and finally, when we are applying this into simultaneous equilibrium, which is when one species is present in two different equilibria in the same container, the concentration of the species must be same in both the equilibria. We applied that. Also, one important approximation which we had done, that was, if there is some weak acid Ka, it is hardly going into the forward direction. Equilibrium lies mainly in the backward direction. When we are talking about the reverse reaction of it, that will be almost going to completion. Hardly Hx will remain undissociated. So these two things put together, we have tried solving this question. So the two expressions, S1 at pH 7, S2 at pH 2, we have got in the terms of Ksp and Ka. Simplifying those two equations, like S2 by S1, we divided basically those two. So Ksp term got cancelled out. Only the term which was left as Ka, and that simplification gave us K as equal to 10 raised to power minus 4. So this is the question. Enough of the discussion. Time to say thank you. Bye bye. Stay tuned and keep liking and subscribing. Although this is going to be a very long discussion, anyone who is seeing these videos for the first time, in spite of not knowing anything in the particular topic, they can have the complete in-depth knowledge of all the concepts which can be involved, which can be associated in the question. And the idea is to give you a complete, exhaustive information about one particular question, which any of the options may be related to. That's all for now in this video. Thank you. Bye bye. Take care. Keep liking and subscribing the videos.